Resource Responsible Use of Recycled Tire Rubber in Asphalt Pavements. This presentation was prepared by Galen Baumgartner under the Development and Deployment of Innovative Asphalt Pavement Technologies Cooperative Agreement with the University of Nevada, Reno. Presenting today is Galen Baumgartner of Paragon Technical Services, Inc. of Jackson, Mississippi. This material is disseminated under the sponsorship of the U.S. Department of Transportation in the interest of information exchange under the cooperative agreement number listed. The U.S. government assumes no liability for the use of the information. The U.S. government does not endorse products or manufacturers. Trademarks or manufacturers' names appear in this material only because they are considered essential to the objective of the material. They are included for informational purposes only and are not intended to reflect a preference, approval, or endorsement of any one product or entity. This presentation is arranged in 5 sections corresponding to the selected major headings of the Companion Resource Responsible Use of Recycled Tire Rubber in Asphalt Pavements Technical Report. First, a brief introduction will be presented, followed by a section of background information. Section 3, Specifications and Testing of GTR Modified Asphalt Binders, discusses binder specifications applicable to the wet process GTR Modified Asphalt Binders with respect to current AASHTO M320 and AASHTO M332 performance grade specifications. Dry process GTR Modified Asphalt mixtures are discussed based on mixture testing schemes such as the Balanced Mixture Design BMD approach. Section 4, Asphalt mixture considerations are discussed with respect to expected performance of wet process and dry process GTR modified asphalt in 3 general mixture types: dense graded, gap graded, and open graded mixtures. Section 5, a summary, provides summary and comments and discussion. First, a brief introduction. Recycling is the process of converting waste materials into new materials or objects. It is an alternative to conventional waste disposal that can save material and reduce environmental impact. Recycling of rubber from waste tires is commonly referred to as recycled tire rubber or RTR. When used to modify asphalt binders and mixtures, it is referred to as ground tire rubber or GTR. Whether through binder or mixture modification, incorporation of GTR into asphalt pavements is an attractive alternative addressing engineering, economic, and environmental issues. The Federal Highway Administration established the FHWA Recycle Materials Policy regarding sustainable infrastructure in 2006. The FHWA policy states that recycling and reuse can offer triune benefits of engineering, economic, and environmental impact. As stated, the Recycle Materials Policy regarding sustainable infrastructure was established by the Federal Highway Administration in 2006. The policy states that recycling and reuse can offer triune benefits of engineering, economic, and environmental impact. Comparatively, the American Society of Civil Engineers states that sustainability is made up of environmental, social, and economic needs referred to as the triple bottom line. Pavements with longer service lives should involve less maintenance and are environmentally friendly from the perspective that they involve less greenhouse gas, generating less attention per unit of use. Pavements with longer service lives are more economical and more efficiently serve public needs, which increases social well-being. The primary objective of this report is to provide knowledge for resource responsible use of recycled tire rubber in production of asphalt pavements and to promote sustainable use of recycled tire rubber in asphalt pavements. Technical information is given on the background of recycled tire rubber use in asphalt pavements and information related to specifications and testing of GTR modified asphalt binders, as well as considerations for GTR modified asphalt mixture design. This project is sponsored by the Federal Highway Administration Project Deployment and Development of Innovative Asphalt Pavement Technologies, specifically related to resource responsible use of materials in flexible pavement. An accompanying technical report entitled Resource Responsible Use of Recycled Rubber in Asphalt Pavement is also available at the UNR website. Some brief background information. This brief background discussion will be broken down into sub-discussions of tire components, waste tire issues, and a historic perspective of GTR usage in asphalt pavements, current usage of GTR modified binders and mixtures, rubber modified asphalt processing technologies, and a summary of these technologies. Let's discuss typical tire components. Large amounts of polymers such as natural rubber and synthetic polymers such as styrene butadiene rubber or SBR, ethylene propylene diene monomer or EPDM rubber, and butyl rubber, collectively referred to as rubber, are used in production of pneumatic tires for passenger cars, trucks, and aircraft, among others. The rubber makes up approximately 40+% of the total tire composition, with the natural and synthetic rubber or natural rubber and synthetic rubber typically being used for tread compounds, the ethylene propylene diene monomer or EPDM used for sidewall compounds, and butyl rubber used as the inner liner of the tire due to its impermeability of air. Almost the entire amount of original rubber from waste tires is discarded, which necessitates a very long time for natural degradation. Disposal of waste polymers is a serious environmental concern as polymeric materials do not decompose easily. This poses two major challenges: waste of valuable rubber and environmental pollution due to disposal of waste tires. In 2017, as reported in the accompanying technical report to this presentation, the U.S. Tire Manufacturers Association reported that markets for scrap tires were consuming just over 3.4 million tons, or 81.4% of the estimated 4.2 million tons of scrap tires generated annually. The three largest scrap tire markets in 2017 were tire-derived fuel at 50.9%, consisting of cement kiln, pulp and paper, and industrial boiler applications; ground tire rubber at 29.7%, used in asphalt modification, automotive products, molded extruded products, playground and mulch, and sports surface applications; and civil engineering at 9.3%, including tire shreds used in road and landfill construction, septic tank leach fields, and other construction applications. Recycling of waste rubber from tires into GTR involves grinding a reduction of the rubber into smaller particle size, which results in an increase of surface area. The rubber grinding industry classifies GTR according to the particle size as rubber which is 2.0 millimeters tin mesh and smaller. The typical sizes of GTR used in modified asphalt binders and mixtures for pavement construction range from about 1.5 millimeters or 1,500 microns down to 0.42 millimeters or 420 microns. That's about 14 mesh to 40 mesh. With limited use sizes as small as 177 microns or 80 mesh and 125 microns or 120 mesh. The GTR market is reported at slightly more than 1 million tons, or about 62 million scrap tires. GTR modified asphalt pavements represent 11.7%, or approximately 119,000 tons, 7.2 million scrap tires. This is the GTR share of the total GTR. This is the asphalt share of the total GTR market. Research on GTR modified asphalt binders over the last 50 years has shown favorable impacts of GTR modification. GTR ranks second among the most common asphalt polymer modifiers behind styrene butadiene styrene, SBS block copolymers. Modern GTR use in paving began in the early 1960s with a highly elastic asphalt rubber, or AR. The work expanded into larger chip seal projects along with other crack relief interlayers and open graded surface courses. During the 2 decades following, AR materials increased as they proved useful in various pavement maintenance functional applications, including asphalt pavement. But by far the greatest utilization during this time frame was maintenance applications. During the same time frame, versions of dry mixture addition of GTR to asphalt mixtures posed more of an issue than dry processes employed today. These systems were collectively referred to as rubber modified asphalt concrete, or RUMAC, according to Dr. Mark Buncher in 1995. The primary difference in the dry process technology of the 1960s and the 1970s compared to today's dry process technology relates to GTR particle size and dosage, where in the earlier versions, tin mesh rubber was used at a loading of 3% by weight of the mixture. And today, the mixtures consist of smaller size rubber of 30 mesh at about 0.5% by weight of the mixture. Additionally, co-additives that aid in mixing, placement, and compaction have been employed today. These additives have included processing aids from the tire manufacturing industry, Fischer-Tropsch waxes, and Steramid waxes. As of July 2021, a review of state DOT published specifications revealed that only 12 states currently publish specifications allowing GTR modified asphalt binders for use in construction of asphalt pavements. The National Asphalt Pavements Association recently reported that 21 producers from 11 states indicated using GTR in some asphalt mixtures. The 20,000 tons of GTR used, reported by NAPA, is about 17% of the 119,000 pounds of GTR reported by the U.S. Tire Manufacturers Association to be used in modified asphalt binders. The NAPA report did not include use of GTR in surface treatment such as chip seals, which is a major source of consumption. NAPA reported that approximately 59% of the total asphalt mixture tonnage using GTR was in California, which mandates widespread use of GTR in asphalt pavements. This is not a federal requirement. California is by far the largest user of GTR modified asphalt binder, with uses being directed by PRC 42703. The California DOT, Caltrans, requires that GTR be derived from automobile and truck tires only, that GTR binders be homogeneous, GTR modified binders may not contain visible rubber particles, and GTR modified binders contain a minimum of 10% GTR. Arizona, the second largest user of GTR modified asphalt binders, has two different specifications. Chrome rubber modified asphalt, or CRA, consisting of GTR modified binders with 20% minimum GTR content produced using the AR technology, and PG graded ASTO M320 for hybrid GTR produced by rubber modified binder, or RMB technology, with a minimum of 8% GTR and 2% SBS. Arizona's hybrid GTR modified binder specifications are designated as PG 6428 TR+, PG 7022 TR+, and PG 7622 TR+. To provide an understanding of the processing technologies discussed, this figure presents a chronology of GTR uses in asphalt binders and mixtures in the U.S. Currently, there are two primary processes of incorporating GTR into asphalt binders and mixtures, referred to as either the wet or dry process. The wet process blends GTR with asphalt with one of two technologies. It is done either on-site at the asphalt mixture plant, asphalt rubber, or at the asphalt binder supply terminal, rubber modified binder, with a prescribed minimum reaction time or minimum acceptance specifications prior to mixing the GTR modified asphalt binder with aggregates. The dry process incorporates GTR directly into the asphalt mixture during production. This is usually done by adding the GTR directly to the aggregate in the asphalt plant mixing drum prior to introducing the asphalt binder. These three technologies will be discussed in the following slides. Asphalt rubber, or AR, is defined here as an asphalt binder in various types of flexible pavement construction, including surface treatments and asphalt mixtures, consisting of blending asphalt binder, ground tire rubber, and certain additives in which the rubber component is at least 15% by weight of the total blend and has reacted in the asphalt binder sufficiently to cause swelling of the rubber particles. Other names for this technology include, with appropriate acronyms, the McDonald process, Arizona chrome rubber, wet process rubber, recycled tire rubber modified bitumen, asphalt rubber binder, bitumen rubber binder, chrome rubber binder, and batch blending. Rubber modified binder, or RMB. Rubber modified binder, or RMB, is defined as a version of the wet process where ground tire rubber is blended with asphalt binder at the refinery or at the asphalt binder storage and distribution terminal and transported to the asphalt mix plant or job site for use. These blends may contain from 5 to 12% GTR by total asphalt binder mass. Some hybrid RMB binders may contain polymers such as styrene butadiene, styrene, SBS in addition to GTR. Other names for this technology include, with appropriate acronyms, terminal blend, terminal blended rubberized asphalt, recycled tire rubber modified bitumen, rubber modified binder, hybrid rubber binder, and the Wright process. Dry process rubber. Dry process rubber is defined as a process where hot mix asphalt mixture is modified with ground tire rubber using GTR as an aggregate/binder modifier, which is incorporated into the aggregate prior to mixing with asphalt binder, producing a GTR modified hot mix asphalt mixture. GTR used in this technology is generally less than 0.6 millimeters or 30 mesh. Other names for this technology include, with appropriate acronyms, dry process rubber and belt add modifier. Specifications and testing of GTR modified asphalt binder. Since GTR modified asphalt binders are non-homogeneous, dispersed rubber particles tend to confound conventional characterization by penetration and absolute viscosity. Non-standard procedures have been used to attempt to quantify the physical properties of GTR modified asphalt binders. Agency specifications may vary in format but generally have common components describing the type of product or process, materials, construction requirements, method of measurement, and basis for payment. Acceptance specifications for GTR modified asphalt binders primarily include test results to characterize stiffness of the asphalt binder with respect to expected in-use conditions, complemented by tests to ensure safety, consistency, and retention of properties with aging. Separation or settlement of GTR from asphalt during storage is a common concern. This is primarily due to issues with buildup of GTR in storage tanks with intermittent or sporadic use of GTR modified binders. Precautions and measures can be used to reduce or eliminate settlement issues. Specifications and testing of wet process GTR modified asphalt binders. AASHTO standard specification M320 and M332 may be employed for wet process GTR modified asphalt binders. Modifications to dynamic shear rheometer methods such as increased gap and concentric cylinder geometries have been used to address GTR particle size effects. Increased gaps and alternative geometries allow adherence to the standard specification. Specifications and testing of dry process GTR modified asphalt mixtures. Specifications and certification of dry process GTR modified mixtures is not as straightforward as with the wet processes. While some agencies have specified binder be extracted from mixtures for subsequent binder testing, there are concerns with this practice. Two concerns are posed with testing of extracted binder from GTR modified mixtures. One, is the GTR totally recovered from the mixture along with the asphalt binder? GTR is not totally soluble in any solvent due to SBR content. Two, does solvent extraction aid in better incorporation of the rubber and asphalt compared to the actual field performance? Balanced mixture design, or BMD, mixture testing schemes may be more appropriate for evaluation of dry process rubber modified mixtures. Asphalt mixture considerations. GTR modified asphalt binders have been successfully used in the three general mixture types: dense graded, gap graded, and open graded mixtures. Mixture design volumetrics are important in design of mixtures containing GTR modified asphalt binder or dry added rubber. However, volumetric mixture design procedures may not provide mixture performance desired. It is important to consider the rubber component of the binder and how much it affects volumetrics. The BMD approach may be more suited for a design of GTR modified systems. Asphalt mixture considerations for wet process dense graded mixtures. The three common mix design methods, Marshall, Beam, and Superpave, have been used to design dense graded mixtures with GTR modified binders. In dense graded mixtures, GTR modified binders generally increase optimum binder content and lower laboratory stability compared to conventional asphalt dense graded mixtures. This is generally a result of AR binder, or in the case of RMB, having a higher viscosity relative to conventional asphalt binder, preventing close packing of the aggregate, thereby needing more binder to get the same level of voids in the total mixture, or VTM. Use of AR binders with higher GTR concentrations of 15 to 20% is not common in DGA but may occur. GTR used in dense graded mixtures is typically in the form of AR binders with reduced GTR content, less than 10%, or RMB technology of similar GTR concentrations. Asphalt mixture considerations, wet process for gap graded mixtures. The three general mix design methods, Marshall, Beam, and Superpave, have been used for gap graded mixture design. Gap graded mixtures are generally used with AR technology in place of dense graded mixtures. GTR concentrations may be in the 15 to 22% range. Gap grading generally consists of removing a portion of the fine aggregate to allow room for rubber particles within the gradation. Typical binder contents of gap graded mixtures are in the 6 to 8% range. Asphalt mixture considerations for wet process open graded friction coarse mixtures, or OGFC mixtures. Open graded asphalt mixtures are more common with wet process GTR, modified asphalt binder, particularly with AR technology. A common test for OGFC and SMA is binder drain down to ensure that binder does not flow off the aggregate during normal production, placement, and compaction. Stabilizing agents are often used to aid in resistance to asphalt binder drain down. Sometimes warm mix additives may be used with GTR modified systems, allowing lower temperature, which aids in prevention of drain down. It is important to consider the contribution of binder stabilizing agents to mixture durability before foregoing use of these stabilizing agents. Asphalt mixture considerations for the dry process. Dry process GTR modified asphalt mixtures have been designed using standard mix design methods. Criteria for selection of optimum asphalt binder content may be different than typically used in these methods. Laboratory designed mixtures are prepared by pre-blending heated dry aggregates and rubber followed by addition of the asphalt binder. Laboratory stability and stiffness values of dry process modified asphalt mixtures have been reported to be lower than values of conventional mixtures. Summary and discussion. There are several common repurposing methods to effectively reuse recycled tire rubber. As seen, recycling of rubber from old tires includes the three largest scrap tire markets of tire-derived fuel, ground tire rubber, and civil engineering applications. GTR is the second highest consumer of recycled tire rubber, with uses in several applications to include asphalt binder and asphalt mixture modification for asphalt pavement construction. As an accepted practice of asphalt production, GTR modified asphalt binder and GTR modified asphalt mixture consumes about 12% of the total GTR segment of the recycled tire rubber market. Asphalt modification with GTR is well established and can reduce the number of waste tires disposed of in landfills while providing high-performance pavements. Growth and use of GTR modified asphalt can be credited to construction of high-performance asphalt pavements. Dry process addition of GTR to asphalt mixtures, while it is in its infancy, has generated promising reports. At this time, I thank you for your attention. Don't forget to go to the University of Nevada, Reno website and get a copy of Resource Responsible Use of Recycled Tire Rubber in Asphalt Pavements. This could be a very valuable document for training and education. Thank you, and let's pause for questions and discussion.